Hello everybody, welcome to the Ultimate Physics channel. The topic of this video is quantization of matter and radiation. What is quantization? Let us begin with the definition of quantization. Quantization refers to the idea that a physical quantity can only have certain discrete values. It essentially means that the physical quantity that is said to be quantized cannot take any arbitrary value. The values that it can take cannot be continuous. That's what we mean by discrete. Now, this also implies that the said physical quantity can always be expressed as an integer times a fundamental quantity. This fundamental quantity is called as the quantum of that quantity. The plural of the word quantum is quanta. So in physics, we often use these two terms interchangeably, namely discretization and quantization. These two are synonymous. And the word quantum is used to refer to the smallest portion of that physical quantity, and the plural of which is quanta. So suppose we have in this definition a total charge, let us say Q. If Q is the total charge, then we express the total charge as integer times the quantum of that physical quantity that is charged, which is E in this case. This is an example that describes quantization or discretization. Let us now deal with the idea of quantization with some concrete examples. Let us take the example of matter itself. The idea that matter is composed of atoms is millennia old. Early Greek philosophers believed that matter is made up of atoms, but then for them the atoms were featureless and indivisible objects. The modern physicist, on the other hand, suspected the atoms to be divisible, and so he tried to probe the atom. And he eventually succeeded in prying open the atom, as a result of which he understood that matter is quantized. This prying open the atom led to the discovery of the nucleus and eventually the nuclear structure. The electrons were known by then, and so he learned that charge also is quantized. This equation refers to that. The fundamental quantum of charge is E, which happens to be the magnitude of the charge of the electron as well, albeit with a negative sign. So he could express the charge of any other object in terms of the electron charge. If Q is the charge carried by an object, then we could express Q as Q is equal to n times E, where n is an integer and n could also be called as the quantum number here. This is what J.J. Thomson discovered, and Millikan verified this later by performing the famous oil drop experiment. The discovery of nuclear structure and its composition posed serious questions about the quantum of matter. The crux of these questions is regarding the ultimate building block of matter. As per our current understanding, quarks and leptons can be considered as the quanta of matter. But the truly remarkable discovery of mankind has to be the quantization of energy, or the quantization of radiation. When we say quantization of energy, we imply two things. The first is the quantization of energy in general. The next idea is the quantization of light in particular. So essentially, both matter and radiation, of which the observable universe is made of, are quantized. Coming to the quantization of energy, it was Max Planck who first proposed that energy is quantized. He This while trying to provide a theoretical explanation for the black body spectrum. he had to assume that whatever fundamental entities of which the black body is made of, they exchange energy only in terms of certain packets called quanta. So the energy exchange does not happen in any arbitrary quantity. These fundamental entities of which the black body is made of were thought to be oscillators, and their frequency of oscillation is proportional to their energy. Thus, the energy exchanged by these oscillators could be expressed as, for example, let us say total energy E is equal to n times h nu, where h is the Planck's constant, nu is the frequency of oscillation of the oscillators, and n is the quantum number here. So this expression simply captures the quantization of energy or radiation. This profound insight led to the birth of quantum mechanics. Soon it was understood, thanks to the works of people like Niels Bohr and Rutherford, the energy in the atoms is quantized. The energy exchanged between atoms as well as the energy levels at which the electrons reside in an atom are quantized. So, when an electron in an atom gets excited, it can move only to predetermined energy levels for occupation. This also implied quantization of angular momentum, where Bohr assumed that the total angular momentum L could be expressed as some quantum number times h over 2 pi. This also can be expressed as nh cut or nh cross. This crude model provided by Bohr led to the idea of quantization of angular momentum. Extending this quantization of energy in general to light in particular is not an easy task for ordinary mortals, but not for Albert Einstein. He could immediately see the connection when he tried to explain the photoelectric effect. In order to understand the dependence of emission of electrons on the frequency of the incident radiation rather than on the intensity of the incident radiation, Einstein theorized the quantization of light. He simply could connect the dots and draw the line. That is the hallmark of a genius, and Einstein sure was one. And again, Millikan was involved in experimentally verifying the photoelectric theory by measuring the Planck's constant using the photoelectric effect. Thus born the remarkable idea of quantization and the subject of quantum mechanics itself. That brings us to the conclusion of this video. Hope to catch up with you soon on another interesting video. Until then, it's bye from me. Thank you.